Outer space holds a weapon 100 million times more powerful than an atomic bomb. One strike, and it could black out a continent. From the space age to the Stone Age, in a flash. The weapon isn't man-made. It's our sun.
It's always a question of when the next one will happen. It's not a question of will they suddenly go away.
We've been hit before. We're in its sights again. Quebec, March 13th, 1989. The city is in the grip of winter. Temperatures are below freezing. Suddenly at 2:44 a.m., a 100-ton transformer on the Montreal power grid overloads. Blackout. The city is plunged into darkness. 6 million people left powerless. Astronomer Sten Odenwald explains how the night unfolds.
All the lights went out, quite literally. It only took about 90 seconds for fully operational to complete blackout conditions.
At dawn, the thermometer reads just 8 degrees, and the power's still out. Life or death work runs on emergency generators. The blackout lasts 12 hours. But the disaster could have been much worse. If not for a few transformers in the US, millions of Americans might have lost power too.
With only a couple of more components damaged, the entire East Coast would probably have gone down as well.
But what caused the transformers to overload so violently? Why did Quebec plunge into darkness? This wasn't a terrorist attack or human error. The culprit wasn't of the Earth. It was the result of a gigantic explosion 93 million miles away on the sun. Three days before the power network collapses, astronomers at the Space Weather Prediction Center in Colorado monitor an active region on the sun, when suddenly a giant explosion bursts from its surface. A white flash thousands of miles across and millions of degrees hot. 93 million miles later, a huge wave of radiation slams into Earth's atmosphere. Colored lights dance across the night sky from Alaska to Mexico. Quebec is hit by an invisible but immense natural phenomenon. A solar storm. An explosion of the sun so awesome, and a wave of energy so huge, it's almost impossible to measure. Space weather scientist Joe Kunches is blown away by the scale of these storms.
Billions or trillions of tons of matter is thrown off the sun at 1 million or so miles per hour. And I think it bodes towards the difference between terrestrial weather scales, where you might have wind speeds in the extreme of hundreds of miles an hour in a very strong hurricane or a tornado, to looking out at the solar wind, and the solar wind typically is 1 million miles per hour.
The solar storm that hit Quebec is the worst in living memory. But worse may strike the Earth in the future. And next time, we might not be so lucky. The sun is capable of producing storms that could black out whole continents. North America would be crippled.
Losing the electric power grid, even temporarily over an entire continent, is a major disruption to the way we operate in the 21st century.
Our lives are more complex and technologically advanced than ever before. But the freedom technology brings us could also be our downfall. Anything relying on the power grid when a solar storm strikes is vulnerable. But what causes a solar storm? How do they wreak so much havoc here on Earth? And is there any way to protect ourselves from future attacks? Scientists need to unravel the mysteries surrounding the sun and reveal the anatomy of a solar storm. The investigation begins 93 million miles away. The Sun is a 900,000-mile-wide ball of gas, mainly hydrogen. It's so vast, you could fit over 1 million Earths inside it, with room to spare. All the Sun's energy is generated deep within its heart, at the core. Temperatures here reach 27 million degrees, thousands of times hotter than Earth's most extreme forest fires. Every second, millions of tons of hydrogen are converted into helium. This nuclear fusion produces over 5 million tons of energy. The Sun radiates more energy in 1 second than the world has used since time began. The byproduct of all this energy is vast amounts of magnetism. Huge magnetic fields loop across the surface. They bubble up from the core and punch hundreds of thousands of miles into the solar atmosphere before plunging back down again. These arcs are so vast, the Earth could fly through one, with 100,000 miles to spare on each side. On planets like the Earth, every part makes a full revolution around its axis each day. But the Sun is a dynamic ball of gas. Its equator rotates in 25 days, but the poles take 35 days. The magnetic loops stretch and distort as it turns. Along each loop flow billions of tons of superheated plasma, electrically charged protons and electrons. A single loop contains the energy equivalent to 10 million volcanoes erupting at once. These loops are sometimes the first sign of an impending solar storm. Professor Paul Bellin wants to find out how these loops lead to a solar storm. So he recreates the surface of the Sun in his lab.
We have the main ingredients of what goes on in the Sun. We set up a magnetic field that is arched. We have a plasma there that can conduct electricity just like the plasma on the Sun. And we drive an electric current along the arch just like on the Sun.
With all the ingredients of the Sun in place, Bellin passes an electric charge through the experiment. Bellin's work shows these arcs are unstable. They twist and stretch in all directions. When they collide, they short circuit, like crossed wires. All their energy is released in a spark, a white-hot flash. The same phenomenon we see on the Sun. A solar flare.
It's a little bit like seeing a hurricane develop. You can see the precursors of something that might blow up on the Sun. You have currents, magnetic fields, the currents make forces, and if they add up in the right way, you can get very powerful forces that can cause these structures to blow up.
Bellin's lab flares release only a small amount of energy. If the energy packed into a solar flare was unleashed on Earth, the explosion could level whole cities. The shock waves would be felt on the other side of the Earth. Nearly all life would be wiped out. far stronger than the world's nuclear arsenal.
The smallest of the flares are more than 1 million nuclear bombs going off. The largest ones are 1 million times 1 million of these bombs going off.
Dr. Carol Schreiber studies the power of solar flares.
A large flare is a vast amount of energy. It has no counterpart on Earth.
One solar flare packs enough energy to power America for thousands of years. In 1997, NASA captures this image of the sun's surface the moment after a solar flare explodes. It shows a shock wave, a ripple, racing thousands of miles across the surface. It travels so fast, it could circle the Earth in less than a minute. A solar flare packs a huge punch, but it isn't responsible for Quebec's power failure. It is the first stage of a devastating onslaught. Like the flash from a gun, it's the bullet that follows which causes the damage. Behind nearly all solar flares is a gigantic cloud of radiation, and in its sights, Earth. But its first victims are in outer space. For years, space scientists have known of the threat posed by solar storms. But the sun is unpredictable, and sometimes even NASA can be taken by surprise. May 14th, 1973. America's first space station, Skylab, launches.
Moving up. Skylab has cleared the tower.
Its mission: to prove that humans can live for long periods of time in space, and to expand our view of distant planets and stars. In total, 9 astronauts visit the station. The longest stay is 84 days. But Skylab is plagued with mechanical problems, and in 1974, it is abandoned by its crew and left to await repair. But in 1979, something knocks Skylab out of space. Scientists discover that between 1974 and 79, the sun fires a barrage of solar flares toward Skylab. But it isn't the flares that bring the spacecraft down. It's what follows. Minutes behind each flare is a gigantic wave of radiation. The wave contains huge amounts of electromagnetic energy, X-rays and gamma rays straight from the surface of the sun. The wave travels at the speed of light and smashes into the Earth's upper atmosphere, which heats and expands.
Solar storms, especially solar flares, dump enormous amounts of energy into the upper atmosphere. The upper atmosphere responds by heating up from 500 degrees to 1500 degrees, and that also causes it to expand out by up to 1,000 miles.
The swollen atmosphere envelops Skylab. The space station is suddenly surrounded by air, where once there was nothing but space. Air drag slows the satellite down, and it begins to fall out of orbit. In July 1979, Skylab crashes to Earth. Luckily, much of Skylab burned up on re-entry. Without regular boosts, thousands of satellites could suffer the same fate as Skylab. The multi-billion-dollar International Space Station is at risk.
Even the International Space Station has to worry about solar storms. It typically loses about 75 yards of altitude every day, and during solar storms, it can lose quite a bit more than that.